Today I'm going to guide you through some of these problems. So first of all, turn to page 11, and we're just going to do number 1 on page 11. So it's launched at 20 meters per second and an angle of 60 degrees. And you want to know the projectile's maximum height using energy methods. So we could find the maximum height using the projectile equations and things that we've done before, but now we're going to look at using energy. So the key that you should always write on every question that you see that has anything to do with energy, or if you're stuck, write energy before equals the energy after. So then what energy is there beforehand? Beforehand there's just kinetic energy. We'll just call that K. And then afterwards you have potential energy, which is U for potential energy. And it's gravitational potential energy, so it's UG, plus you do have some kinetic energy, but only in the horizontal direction, because at the top it stops vertically, so you only have horizontal kinetic velocity there. Also, one thing is where your gravitational potential energy is 0. So you gotta set what your baseline is that you're referencing everything in regards to. So beforehand you had 1/2, the mass is, we don't know. The velocity is 20. You don't do it at an angle because it is a scalar. So you're just considering all of the energy before equals all of the energy after. And then it goes to a height of m. We can just use 10, makes things a lot easier. We want to know how high it gets, that's what we're solving for. Now the horizontal velocity is the same as it was at the beginning, because remember that the horizontal part in a projectile stays the same. The horizontal component would just be 20 cosine of 60. We're squaring that. Cosine of 60 is one of the things you should know. Sine of 30 equals cosine of 60. They're both 1/2. So 20 cosine of 60 is just 10. 10 squared is 100. But yeah, all the masses cancel. That's going to happen a lot actually in conservation of energy, because unless there's a spring, because that one doesn't have mass. But when it's just kinetic and gravitational potential, there's a mass term in all of them, so they would all cancel out. This is 10H, this is 200, 15 meters. Okay, on to number 2 on the same page. Again, we write energy before equals energy after. This should get as tiring as writing F equals ma, because you should always be writing that on your force problems. So A says, what is the velocity of the car at position B? Position B, I'm going to draw this on here for us. This, remember what I said I want you to always mark? That's where your gravitational potential energy equals 0. We know the height at the beginning. So we just take our energy at the beginning equals our energy at the end. So at the beginning there's only potential energy, so which is 200 g, and the height is 60. And afterwards, or the B position, there's only gravitational potential, so it's m. There's only kinetic, so it's 1/2 m v squared, and we want to know that velocity. The masses cancel, so it's 600 times 2, I just moved that over there, equals v squared. So v is the square root of 1200, which is 34.64 meters per second. So B, we want to find the velocity at position C, which is over here. We talked about before that if this is the radius and this is the radius, we're assuming that that is at the radius position, so that height is the same as the radius, which is 20 meters. So I want you to pause and try this again yourself. Find B, which is asking the velocity at position C. So what you should have is the same initial conditions, 200 times 10 times 60 equals 1/2 mv squared, but you also have potential at this point. So you also have 200 times 10 times 20, because it's 20, the height is 20. Now I want you to always write the mass, even though it's canceling out in these, because you always want to show all of your work. So it's 600 equals 1/2 v squared. This is a 20 that you can't read, plus 200. So it's 400 times 2, so 800, so square root of 800, which is 28.3. Okay, part C. You're drawing the free body diagram at position C, which is on the side of the circle right here. So you've got your weight straight down, and then the normal force, which is the force of the track on the car, is just straight towards the center because it's going around a circle. So in a circle, you have the fact that your force and your acceleration are always towards the center. It's traveling around usually at a constant velocity. It's traveling around usually at a constant speed, but the velocity is changing because the direction is towards the center. So it's accelerating because it's changing direction. And part D, we want to find the velocity at position D, which is at the top. So again, you should be able to do this one. So pause the video and everyone try this one again. So you should have same beginning as just that's the total energy because that's the only one you know at the top of the ramp. And now we know G, and the height is 40 because it's the diameter of it, plus 1/2 mv squared, the masses cancel. 600 equals 400 plus 1/2 v squared. So 200 times 2 is 400, and the square root of 400 is 20. So E is asking for a force. Anytime it mentions force or equilibrium, you should automatically draw a free body diagram. So it didn't ask us to draw the free body diagram at D, but let's do that anyway. It's at the top now. So at the top, the force down is still your weight. And your normal force is towards the center, so that's also down. So both of your forces are pointed down. So your net force equals the normal force plus the weight. Now, since it's a circle, your net force also equals, for centripetal force, the equation is mv squared over r. So that equals mv squared over r. So we want to know the normal force, which is the force of the track on the car. So it's 200, the velocity at d we just solved for earlier was 20. The radius is 20 minus 200 times 10. One of these 20s cancels one of those. So it's 4,000 minus 2,000. So your normal force is 2,000. And F, for F it says, after completing the loop, the roller coaster car is traveling horizontally at velocity v0 and subjected to a braking force of negative kV. Develop an integral that could be used to evaluate the velocity of the car along the horizontal track. Alright, everyone buckle your seatbelts because it's going to get exciting here. So the other thing besides this equation that was given to us is, again, name times c force involved, draw the theoretical if you can, this one you can't really, and write net force equals ma. So if your F equals negative kV, then, and your F equals ma, then just set those equal, you get negative kV equals ma. Well, acceleration is the derivative of velocity, so we could put in dv dt. You want to put the terms together that match. So we're going to put all the constants on the left and the time on the left, and then we're going to put all the velocity ones together on the right. It could be opposite, just you want to get them together with the things that make sense. So I move stuff around to get the same type of terms on the same side. So now we're going to integrate both sides. Remember that the integral of a constant, you just pull out the constant. So that's just negative k over m. And then there's no t in here, so basically you have a 0. And so you have an x to the 0. And then you add 1, so it's just x, but in this case t. So since there's no t there, it's as if you have a t to the 0. You're integrating in terms of t, so you gotta make sure you use t on that side. And then on the other side, you're integrating in terms of v. You do have a 1 over v here. And remember that the integral of 1 over v is natural log. And we're doing a definite integral, so I should have put definite things on here. For the time one, it's going from 0 to t. And for the v, you're going from v naught to v. You're taking the natural log of v minus the natural log of v naught. To put those together, that's the same thing as v over v naught. We do e to both sides, and that gives you e to the negative kt over m equals v over v naught. And what are we solving for? We're solving for the velocity. So we get v, and we can put of t in terms of t if you want, equals v naught times e to the negative kt over m. So that was actually part 1 and 2. The first one says just develop an integral, so that would just be this part. And then solving it gets you to this answer for a function of velocity. Alright, on to page 12. Number 3, we have a block that is at a distance d, and then we stretch it to 2d and it's not moving. So, a couple things with springs. Equilibrium and not moving mean that your force equals 0. So if you're at the equilibrium position or you're not moving, then your force equals 0. The equilibrium position is in the center, where it's not being stretched or it's not being compressed. So it's in the middle of the range that it can go with, and it's not moving while not being compressed and not being stretched. So A, we want the free body diagram when it's at 2D. It says it's stationary, so we just draw, we got your weight down, your normal force up. Remember to make sure these are from the center. You've got a spring force to the left, and friction opposing that. B, we want to determine the friction force when it's located at 2D. Well, we just said that the net force equals 0. So you've got your friction force equal to your spring force. We want to know the friction force, so just leave that one there. Spring force, the equation is Kx. And K is the constant, that's the spring constant. And X is the distance that it's compressed or stretched. So in this case, how far was it compressed or stretched? Well, it was from D to 2D. So that is a distance of D. So your F, force of friction, will just be K times D because it was stretched a distance of D. Then part C, now it's been stretched to 3D. And it wants to know what the value of mu sub s is. So now it's sliding. Well, once it gets released, but at 3D it's still stationary, it says. So now we're going to use this same idea, that since it's stationary, your forces are balanced, so your force of friction will just equal K times X. Now you've stretched it 2D because it went from D all the way to 3D, so that's a distance of 2D that it was stretched. So your force of friction will be K times 2D. Force of friction is mu times the normal force. The normal force here equals your mg, so it's mu mg equals 2kd. So your mu equals 2k 2kd over mg. Part 2 asks how much potential energy is stored. Now don't be confused, potential energy equation and the force equation for springs can seem really similar. Remember that the force of a spring is kx. The potential energy of a spring is 1/2 kx squared. So in this case we're doing potential energy of the spring. Again, not to be confused with mu sub s. So mu sub s has to have the little tail on it and it's a lowercase. And then potential energy U sub s equals 1/2 kx squared. And the distance that it's being stretched here is 2d. So you get 1/2 k 2d squared. So 2 squared is 4, and 4 divided by 2 is 2, so you get 2kd squared. And don't put units when you're solving for variables, that's just when you have numbers. Okay, part 3, the block is now sliding and you're looking for u or mu sub k. And the problem says mu sub s, but it's a typo. It should say mu sub k because it's moving. And now you're going from moving to stopping. So it's moving from 3D to 2D. And remember that equilibrium was at D. So when you're at 3D, which is where you're starting, you're a distance of 2D. And when you end, you're a distance of D from the origin, or from the equilibrium position. And we're going to do conservation of energy because we're looking for mu. So we always write energy before equals energy after. And we need to consider what kind of energy there is in each case. So what kind of energy do you have beforehand? Well, let's think. Does it have kinetic? No, because you're holding it back and it's not moving. Do you have potential? Spring potential? Yes, because it's attached to a spring. Afterwards, do you have kinetic? No, because it came to a stop again. And you have spring potential. And then there's one other thing. We've got this idea of friction. The friction is doing work. It's slowing it down. That's what's allowing it to stop. And we need to account for that because the work in this case of friction is it's reducing the amount of energy. So you can either subtract it from the left side, the beginning side, or you can add it to the product side. It doesn't matter, it's just whichever one makes more sense to you. So that's the thinking that needs to happen as we set up a conservation of energy. Thinking about all the energy that's possible beforehand and all the energy that's possible afterwards. Now we need to plug some things in. So we can plug in 1/2 k initial position squared equals 1/2 k final position squared. And then the work is the work that's due to friction. And remember the work equation is force times distance. So it's the amount of friction over the distance that you apply the friction. So we can start with that. And then remember that friction equals mu times the normal force. And then to know the normal force, we need to draw the free body diagram, which we should have probably drawn at the beginning. And we can plug in, see these are equal, so we get mg for the normal force. I should say final. Okay, now we need to plug in how far it's compressed or stretched. So let's draw this picture again and try to decipher this. So first of all, it told us that at position D, that's your equilibrium. So that is where it's not stretched or compressed. And then we also have 2D, which was one position it was at, and 3D, which was another position. So our initial position is here at 3D. However, that is being measured from here for some reason, and we want to be measuring it from equilibrium. So the distance to the starting position is actually a distance of 2D. And then the distance to the final position, so it travels for 1D. So we start here, we go for a D, which brings us to right here. And that's a distance of D away from equilibrium. Now I know that can be confusing because there's D, 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 3D, 2D, whatever. So if you guys don't understand, just pause real quick and make sure everybody understands why our initial compression, or stretching in this case, is 2D and our final is 1D. It's because it's the distance from equilibrium. So now we can plug those in, and we have 1/2 K. So the initial position we agree is 2D. The final position is D. So this is 1/2 times 4, so 2kd equals 1/2 kd squared. Sorry, that was squared also. So it's mu mgd. So subtract, since these terms are the same idea, we get 1/2 kd squared equals mu mgd. So one of the d's cancels, and you get mu equals 3/2 kd over mg. That's your kinetic mu. Now part 4 asks, what position does it have its maximum velocity? So the key for maximum velocity is when the acceleration equals 0. And in that case, your force is also going to equal 0. So your net force is your spring force minus your force of friction. So your spring force just equals your force of friction. So spring force is Kx, and force of friction is mu mg. We just solved for mu. So we get Kx equals 3/2 kd over mg times mg. These cancel, the k's cancel, and you get that the distance is 3/2 d. Now that was from the 2D mark. So what we found was we had our equilibrium position, we have 2D, we have 3D. It was released from this point that was 2D away from equilibrium. Remember? So that means that if it traveled 3/2 d away from 3D, then in relation to equilibrium, it's actually 2D minus 3/2 d. And that's because it's 2D, the distance that it was away, minus the distance that it traveled, tells you how far away you are now from the equilibrium position. So this equals 1/2 d. And that's the position in relation to equilibrium that you now are at. So in part 5, we want to find the maximum velocity. So maximum velocity should make you always think of conservation of energy, and you want to maximize it. So you're still starting with spring potential energy because you can't start with anything else. That's what you're doing. You're releasing it from the beginning. And afterwards, you're still going to have kinetic. You're still going to have some spring. And you're still going to have some work. It's just we're going to solve for the velocity now instead of just solving for mu. If we plug these in, we have 1/2 k x initial squared equals 1/2 mv squared plus 1/2 k x final squared plus mu mgd. So the x initial was still 2d. So this distance, I shouldn't have already put a d here. So the distance that it was compressed would be the 1/2 d. And then we need to plug in this distance, which is the distance that it actually moved. Which, remember, if we look at our picture, the distance it moved was this distance, which was 3/2 d. So the position is 1/2 d, and that's how far it's technically stretched or compressed. I guess stretched in this case. But it actually moved 3/2 d away from the 2d mark. So we get 2kd squared equals 1/2 mv squared plus 1/8 kd plus mu mg. Three halves d. And then we solve all this, but in the interest of time, so you have to plug in your mu that you just found and solve it, and you get v equals d over 2 square root of k over m. We're going to do one more problem that's going to give you a good range of kind of what you can see. Obviously it doesn't cover everything that's possible, but it should be a good start. And that's on page 13, it's number 4. Basically you have a pulley, and you've got a block that's on the ground, and a block in the air. And it wants to know the speed of the 3 kilogram block when the 5 kilogram hits the floor. So 5 kilogram is 4 meters above the ground. So what kind of energy is present in the before here? Well, let's set our 0 line for potential energy, that's here. So we write UG equals 0. And the only energy in this system beforehand is of the 5, and it's potential energy. And then after, both blocks will be moving. Since they're connected, they will have the same speed. But they have different amounts of kinetic energy since they have different masses. And now the 3 block will have some potential energy. So now if we plug in, we get 5 times 10 times it's 4 meters high equals 1/2 times 5v squared plus 1/2 times 3v squared plus mg. Now it's going to go up 4 as well. So that's 200 equals 5/2 v squared plus 3/2 v squared plus 120. So you subtract and you get 80 equals 4v squared. So v equals 4.47 meters per second. Now the question also asks for the maximum height. Well, the maximum height is going to be if they're both not moving. So if you could eliminate both of these terms and just know that your initial potential turns all into your final potential. So it all gets converted into just potential energy. So you take your 200 from the potential energy of the 5, and that's going to equal so it'd be 200 divided by 30, which is 6.67 meters. So it didn't matter that there were two different objects. If one was on an incline, the only thing that matters for it being on an incline is if there's friction involved. Then you gotta make sure you take the friction component, or sometimes you'll take a component because you'll know this distance and you'll know the angle, but you won't know the height. So things that you should know from now are, you should know that work equals force times distance. You should know that the spring force is kx. Spring potential energy is 1/2 kx squared. When in doubt, try F equals ma and draw a free body diagram. If it mentions energy, be thinking conservation of energy, so it's your energy before equals your energy after. I want you guys to try some on your own now. So I'd like you to try number 64 and 65 on page, 67. Number 64 and number 67 on page 14. They're worked out in my book, so you can check your answers and make sure you're on the right track. Good luck. See you Friday.